Okay, so I have an example of a length contraction problem, but first we're going to do a time dilation problem. And these problems might seem kind of simple, but there's actually, I think, a good intuitive learning experience doing these two particular problems. So bear with me. One of these problems we've done already, but we're going to review it. The next one isn't too difficult, but I think it'll really help us understand conceptually a little better what's going on, which I think is really important. Okay, so the first problem, we've actually worked through this problem before. The muons, the muons ones where it's going from the atmosphere, a height 100 kilometers up, and it's going to the surface, and you have to find the minimum speed to do that. This is actually, I didn't mention this when I first did the problem, but this is one of the ways we know time dilation is real. So you can either watch the other video or we'll go over it again. So we have, that is as big as it goes. Okay. So we have a proper lifetime of 2.2 microseconds. That's what that little mu is. Man, it's really hard to use a highlighter. I might underline stuff. So they're produced very high speeds in the upper atmosphere when cosmic rays collide with air molecules. And they give us a height L naught, which is 100 kilometers away, in the reference frame of Earth, and find the minimum speed that enables the muons to survive the journey. So just like how we had it earlier, our proper lifetime is 2.2 microseconds. And if you don't understand proper time and proper length, that's mostly what this video is going to help us understand. It's okay if you don't understand it yet, but essentially the proper lifetime is the time where your clock is, it's if you think of the reference frame of where the clock is not moving. So we have these particles moving from the upper part of the atmosphere, so up here, and it's going to move down, 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 a height 100 kilometers down to the surface of the Earth. And what we need to do is we need to find the speed necessary to give us the time dilation where it'll actually make the trip down. Now, our clock is the lifetime of the particles. So the proper lifetime from the muon's perspective, it's stationary and it's the Earth that's moving. So because from that perspective, our clock is staying still, that's our proper time. Now, our proper length is going to be where it looks like the length is at rest, which would be from the Earth's perspective. And if that doesn't make very good sense yet, let's just work through this problem a little bit, and I think it'll make a lot more sense. And then we would say L naught, they give us as 100 kilometers. So it goes to the top of the atmosphere, it travels to the surface. Well, let's see. Our time that it takes to do that is going to be our length over the speed. And our length is 100 kilometers over 3 times 10 to the 8th meters per second, which when you plug that in, you get 330 microseconds. Now, this is from Earth's perspective. This is Earth sees, or I guess Earth measures, right? So this is what the Earth is measuring from their perspective. The length the speed that it's going, all that. So this is what we would measure. Now this is our time dilation. It's dilated. It's a lot longer than the proper time of just 2.2 microseconds. I guess micro is not very big, but the fact that they're not the same, it's big enough of a concern that it becomes relevant in experiment. Okay, now that is the time from the Earth's perspective. Okay? Now, if we remember our equation, we had it written at the top. Delta T is equal to delta T naught, our proper time, all over the square root of 1 minus v squared over c squared, right? Yeah, just making sure it was 100. Okay, well, what we're interested in, this is actually a U. There's a little reason why we use U and not V, but we'll get to that later. So we have to do a little bit of math here. And I'm going to do it onto the side. So delta T times the square root of 1 minus U squared over C squared equals delta T naught, or 1 minus U squared over C squared equals delta T naught squared over delta T squared, or 1 minus delta T naught squared over delta T squared equals U squared over C squared, or U equals the square root of C squared times 1 minus delta T naught squared over delta T squared. Hopefully the algebra is not too bad. You guys are all okay with that? Oops. The square root of C squared is just C. They were given the proper time, delta T naught, so this is what we were given in the question, and then we just found this. And when you plug that in, you get a speed of about 0.99978 c. So about 99% of the speed of light. So these things have to move very, very fast for it to get the type of time dilation that we're seeing, for it to survive this journey. Okay? So hopefully we're okay with that. So now that we did that, and hopefully the algebra makes sense, now that we have that, let's look at this next problem. Consider the point of view of an observer who's moving towards Earth at the same velocity as the muon. In this reference frame, what is the apparent thickness of Earth's atmosphere? So we're thinking, what if somebody was just kind of riding along this path, or an observer? Or you could just think of it as being from the perspective of the muon. Well, here's what we need to understand real quick. Our equation is the first thing to write down, and your length is equal to your rest length, L naught, times 1 minus U squared over C squared square root. And again, L naught is our rest length. So that's the length, the apparent length when you're looking at it from a perspective of rest. So from the muon's point of view, the Earth isn't at rest. It's moving towards it at that speed that we just found at whatever. So the rest would be from Earth's point of view if you're sitting on Earth. So the rest length is just 100 kilometers. And we just found the U, right? And this is why we reviewed it, because we needed to know this, and in case you forgot. So there's that. And again, just trust me here. I know it looks really simple. Okay, that's easy. L naught's just 100 kilometers times the square root of 1 minus the c squareds cancel, so you just get 0.99998 squared. Right, u squared, that's this whole thing squared. So this c squared will cancel with that c squared. And if you are to plug all this in, you'll get about 0.66 kilometers, which is about 660 meters. Now this bit over here is the length contraction. Okay? So this distance is small enough for the muon to reach the surface of the Earth in the 2.2 microseconds. So keep in mind, even though we might measure one time from Earth's perspective, this is the proper time, the 2.2 microseconds. So in order for it to make that distance, the muon must travel a shorter distance because, right, distance is rate times time. So the distance must be smaller if we're going to reach it in a quicker time, right? Distance over rate is our time. So if we're going to reach it in that time, the time's going to be smaller, so either the speed needs to increase or the distance needs to decrease. Okay? So hopefully that kind of makes sense in terms of why that would, in terms of what the muon is actually experiencing. It's the one experiencing the length contraction. Now, and I'm going to do this in a different color because I think it's important. So what Earth, from Earth's perspective, sees as time dilation, that's from Earth's perspective. So Earth, if you remember, we did it. We saw that there was this proper time, but that's not the time that we measure from Earth. Okay? So Earth will see time dilation, but the muon sees as length contraction. I think that's a really interesting concept. That Earth will measure a different time. It'll see time slow down, right? And that's another way that you can make that distance. But for the muon, what it does is it sees, instead of time taking longer, time ticks the same for the muon, or at least it's proper time. And instead, it sees the length shrink. So that's pretty interesting. The next thing I want us to do, and I think this will also help us with understanding the proper time and the proper length and whatnot, is consider a particle moving through a lab. Moving through a lab. Okay? And let's say it has a rest lifetime of 26 nanoseconds. So that's 26 times 10 to the negative 9 seconds. Okay. O1 is at rest relative to the lab. So that we have an observer that's in the lab, and he's just in the lab. He's not moving, he's staying in the lab. And from his point of view, the lab's at rest, he's at rest. And he's going to be observing this. And he measures it to move the particle at u equals 0.913 c, so about 91% the speed of light. Well, if we think of our time dilation, delta t is equal to delta t naught, the proper time, over the square root of 1 minus u squared over c squared. All right, what's the proper time? Well, the first thing is, what's our clock? And the answer is that the clock is the life and death of this particle for however long it lasts. So for that, the proper time would be the just the time that we're given up here. So from that perspective, that's our clock. Now we can find the dilated time if we just plug in our numbers. Equals, we'll keep it in nanoseconds, so 26 over the square root of 1 times 0.913 squared. And if you plug this in, you'll get 63.73 nanoseconds. This is nanoseconds, don't forget that. So notice, well, first off, this is time dilation. And notice it seems to have a longer lifetime from that perspective. So now let's say O2, let's introduce a second observer, O2, moving with the particle. Okay, so from O2's point of view, the particle is at rest. And it's the rest of the lab that's moving. So that goes back to Einstein's postulates. And O2, from its perspective, it's staying still. You can't prove to O2 that he's the one moving, that the particle is the one moving. Maybe it's the lab moving, you know? So O2 is moving with the particle. So from its point of view, the particle's at rest. It's kind of like if you're driving right next to a car at the same speed, it doesn't look like the car's going anywhere. It looks like it's stationary from your perspective. So hopefully that makes sense. Now, the proper lifetime, I guess the proper time, is 26 nanoseconds. So O1, I'll say measures actually, measures the time dilation. Okay, O1 is the one that's measuring the time dilation. Now let's do a little experiment, a little thought experiment. So let's say O1 puts markers at the creation and death of the particle. Kind of grim, but whatever. Okay, so he is putting markers. Let's say it dies here. Let's say it starts here. Okay? Well, we can pretty easily find the distance, right? Where distance equals rate times time, where our rate is 0.913 c. And then our t, which t should we use? Well, this is from the scientist O1's perspective. So we would do the time dilation, which is 63.73 nanoseconds. That's what O1 measures. So if you were to plug this in, the distance is 17.4 meters. So from here to here, it's 17.4 meters. Okay, so hopefully you're okay there. Now let's say, we'll use purple. Let's say a stick is put here. Let's say he puts a stick, a purple stick, whatever, from the start where it was created till where it dies. So the stick is 17.4 meters. Now, since the stick is at rest from the lab's point of view, so from lab's, I'm going to abbreviate it, point of view, 17.41 meters is our proper length. Is our proper length. And hopefully that makes sense. So the stick, the question is, where does it look like the stick's stationary? I guess that's a good way to word it. Well, it looks stationary from O1's point of view because the lab's stationary and everything in the lab itself is stationary. The stick isn't moving, right? It's from this particle's point of view. If this particle were to move along, it would look like the stick's moving towards it or past it in a way. So O2 sees the stick moving. O2 measures the stick moving, particularly at the speed that the particle is moving at 0.913 c. Okay, well, let's see. What would O2 measure? Well, the length is the rest length times 1 minus u squared over c squared, right? And we have everything. So L is our rest length, which we said was 17.4 meters, times the square root of 1 minus, and if you plug it in, you'll still get 0.913 squared. And if you plug that in, you get about 7.1 meters. This is the length of that purple stick from O2's point of view. Isn't that pretty weird? So this purple stick that O1 measures to be 17.4 meters, this particle measures it to be 7.1 meters. So O2 is noticing the length contraction, and O1 is noticing time dilation. So let's make a note of that, because that's another interesting point. O1 measures proper length, right, where the stick is at rest, and time dilation. But look what O2 does. O2 measures proper time. And remember, how do we know what proper time is? Well, we think of what our clock is. And our clock is like the creation and destruction of this particle. So where is our clock look like it's at rest? Well, from the particle's point of view, because the particle thinks it's at rest. So for that reason, it measures the proper time. And length contraction. Okay. So O2, just to make sure we understand, O2 sees our clock. Sees our clock not moving. So because of that, because it sees it not moving, we get proper time. So hopefully that part makes sense. And since O1 sees the stick not moving, we know that's our proper length. So I know that was a little all over the place. We started with a problem we've already done, and we did a pretty simple length contraction problem. But I think hopefully we understand a little bit better how to determine what proper length is, proper time, because if we know that, it becomes a lot easier to work with our equations. We got to do a couple examples to see how it works. We got to do some thought experiments to see, from a particle's point of view, what's shrinking, and from the Earth's point of view, what's the time, and we see how those are related to each other. So hopefully that helps. There's another little meteor problem that I'm hoping to do soon, so maybe that'll come up tomorrow.